shall discuss a very important topic today. It is the p-n junction. You know that on the basis of the p-n junction principles, a large number of devices are made in electronic industry. And if I give you a few name to you, say normal diode. This diode is basically known as the rectifier diode, known as the rectifier. What is rectification? No. It is the conversion from the AC to DC, not from DC to AC. Okay, it is rectifier. That means you will allow it will allow current to flow in one direction. Normally, what happens? Say in AC, such kind of a waveform is seen. That means, on both the positive and negative direction current flows, say, or voltage. Then if you use a p-n junction diode and give input like this, you will get the output as this type of a pulse. So, that means it is not facilitating the flow of current or voltage in both the directions, only you will find that it is in one direction, but you have to use here two diodes, then only the output will be this type of a thing. Otherwise, if you use single diode, the output will be like this, because only the positive half cycle will conduct, not the negative half cycle. Okay. So, now if you consider that a p-n junction diode, then the thing is that how this diode is formed, because now we are in a position to fabricate a p-n junction diode from our knowledge which we have gained in last lectures. Let us take a silicon which is n type. This is an n type silicon. Then we have to make a oxide layer on the silicon. Okay. How this oxide layer is done? This is done by oxidation. This is done by normal oxidation process, and in normal oxidation process generally the material to be oxidized, say in this case the silicon will be oxidized. So, put the sample of silicon in an oven. Okay. The temperature required is 1000 to 1200 degrees centigrade for silicon. Then you have to pass either dry oxygen or vapor plus oxygen, because oxygen can be of two types oxidation. One is the dry oxidation, another is the wet oxidation. This is oxidation. Dry oxidation means when you use the dry oxygen gas, and when you use a water vapor or say with water vapor some dry oxygen, then the oxidation will be an wet oxidation. Now, what is the difference between these two? The difference between these two is that dry oxidation is very thin and its adhesion with the silicon is better than the wet oxidation. That means, the oxide film which is going to be formed using dry oxidation is having better adhesion compared to the wet oxidation film. So, one advantage is better adhesion. Dry, good electrical properties. It is the consequence of the better adhesion, because if the interface is better, then the electrical properties will be better, because the interface will be free from any kind of defects. So, the scattering will be less. Okay. So, these are the advantages of dry oxidation, and so far as the wet oxidation is concerned, the advantage of wet oxidation is that thickness is high. That means, if you want to make a thick oxidation layer, then you have to use the wet oxide. Okay. Thick, that means, if the thickness is larger, then you have to use the wet oxidation. Okay. So, that is the difference between the dry and the wet oxidation. For dry oxidation, better addition is there along with the good electrical property, but for wet oxidation, the thickness can be made larger. That means, thicker oxide layers can be done. Say you want to make some 2 micron, 5 micron, 10 micron oxide layer, then you must use wet oxidation. For dry oxidation, say 0.1 micron, 0.2 micron, some nanometers of thickness, then you can use the dry oxidation. Okay. So, first step is to make the SiO2 layer on N silicon. Say we have started with an N type silicon. Then oxidation is done using a furnace. This is a furnace, this is a quartz board on which the silicon is placed, then this is a vent through which the byproducts will leave from the furnace. This is the temperature heating element which can be controlled, and you send either dry oxygen or water vapor plus oxygen. For dry oxygen, it will be dry oxidation, it will be wet oxidation. So, that is the system. That means, just using a simple furnace, the temperature of the furnace will be 1000 to 1200 degrees centigrade for silicon oxidation, that means, for fabrication of SiO2. Then the next step is to use a photoresist. You see that here we have written that photoresist must be coated on the SiO2 surface. So, first you take the substrate, you make the oxidation on the surface, and above the oxide surface you coat the oxide surface using some photoresist. Right. So, if you use a photoresist, then what will happen? It will coat throughout the surface area. Then you bake it. You bake it at 80 to 100 degrees centigrade. Why this baking is required? After coating with the photoresist, this baking is required because, yes, for drying, exactly, for drying. Okay. Then the next step is you use a mask. You use a mask. Say this is a mask. What is a mask? There are different types of masks used in semiconductor industry, but generally it is a glass plate on which a layer of chromium is deposited. Glass plate coated with chromium. Then on that chromium plated glass there will be the diagram of the circuit, which will be transferred from the computer to the glass plate. So, that means using you first make the circuit diagram on a computer, say using CAD tools, computer aided design tools. Okay. Now, these days there are many simulation softwares or that type of softwares which you can use. First draw the diagram on the computer screen, then transfer the diagram from the computer screen on the glass plate coated with chromium. That means, we have to engrave, that is known as the photograving, not engraving. Here it is done using light. So, photograving is done. So, that is the mask. The mask can be positive, the mask can be negative, different kinds of situations can be there. Then you put that mask on the photoresist coated sample. Here you see that this is the mask. In this mask you see that at the mid portion there is some window type of thing. Then when ultraviolet light incident on the mask, then what happens? Depending on the nature of the photoresist, because photoresist is an ultraviolet sensitive polymer, ultraviolet sensitive chemical. So, when ultraviolet light falls on it, only on the window region it will be in direct contact with the photoresist. On the other parts, the ultraviolet light will be blocked. So, only in the region of the windows the photoresist will be polymerized, it will be hardened basically, it will be polymerized, it will be hardened. On the rest part of it, the photoresist will not be hardening. So, that means, this is your photoresist, then you put a mask on it. Okay. Say that in the mask there is an aperture like this, there is an aperture like this. So, that is a mask. Okay. That is a mask. Now, when ultraviolet light falls on it, only when there is the window, the region, the ultraviolet light will come in direct contact with the photoresist. That portion will be hardened, that portion will be polymerized, and the rest of the portions the ultraviolet light will be blocked by the glass plate. So, it will not be hardened, right. Because our aim is to open an window on the N silicon, that is the region, because when we make a PN junction, I have to define the junction area, I have to define the junction geometry, whether the junction will be 1 micron by 1 micron, whether the junction will be 0.1 micron by 3 micron, that you have to calculate using some equations. That means, when you fabricate a PN junction, you must know what should be the carrier concentration, what should be the area of the junction. So, how to define that area? You have to define the area by this process. Then the polymerization is complete. Now, it is dipped in a solution. If you dip it in a chemical solution, so the portion where polymerization did not take place, that means where the photoresist have not hardened, that portion will be washed away, etched out. Okay. So, this is in the next, in this diagram you see that here this is that region where this is the photoresist coated area, and the wafer after the development will look like this. Development means, since ultraviolet light was used, so it is exposed. So, you put the sample in a developer, it is like photography, you put it in a developer. So, this portion will go out, right. It depends on whether it is positive or negative photoresist, it depends on it is positive or negative photoresist, it is like photography, it is like photography. Then this is the pictorial diagram where the wafer after SiO2 removal, you see that in this region there is SiO2 throughout the surface. Here you see that only this window is defined where there is no SiO2, only SiO2 are there on the left and right parts of the substrate. So, that means I have defined one window having length and breadth of this type for the deposition of p type doping to form a p-n junction. Why? Because I have started with an n type silicon. I have started with an n type silicon. So, for p-n junction you have to dope it with p. Without masking, the whole region will be p type. So, that means the complete surface will be a p-n junction. You do not have any control on it, but as soon as you use this type of a masking, so that means only on this portion there will be p type doping, and the area of the device will be, if the diameter is say 4 centimeter, then the radius is 2 centimeter. So, it will be pi r square, that means pi into 2 square area will be the p-n junction, not the whole p-n junction. Say it is 10 centimeter by 10 centimeter or say 100 centimeter by 100 centimeter, only you define the area where the p-n junction will take place, and that will be your effective area of the device. Because in many applications, in many calculations, you will find that there is a term A, area. So, area of what? Area is not the surface area, area is the device of the area. Yes, you have any question?
After defining solution,
Yeah.
repeat the procedure.
Yes. First you coat it, then your job is to wash out the photoresist material which have not hardened, or if you use a negative photoresist, then which is hardened, right. So, there will be three area. First area there will be say no hardening, then on the middle portion there will be hardening, and on the third portion right side there will be no hardening. Okay. See, it is hardened, it is not hardened, sorry, it is not hardened, it is hardened, it is also not hardened. So, there will be three regions of this planar geometry, this is known as the planar geometry. Then what you have done? Then this portion you have etched out, that means the middle portion you have etched out, yes, right. But it depends on the it can be other way around also. So, depending on the nature of the photoresist, because photoresist can be negative, can be positive, and depending on the developer solution, it is possible that only the hardened region can be washed away or the non hardened region can be washed away. Okay. It exclusively depend on the type of the photoresist, which we are not going to discuss in this class. So, now this portion is see etched out. Okay. So, this is after the development. Development means we have used some developer which is used in photography. Then you see that this portion is having SiO2. Okay. So, if you want to dope silicon, if you want to dope it by p type, then you have to remove silicon oxide. Why? Otherwise, the dopants will not be able to penetrate through the SiO2, because the diffusivity through SiO2 of phosphorus, arsenic, aluminum, boron, etc., is very, very small. So, it will not diffuse. Then you remove SiO2, the wafer after SiO2 removal. This is the wafer after SiO2 removal. Okay. Then you see that here the photoresists were removed. In this diagram, what is the difference between B and C? See, first what is the difference between A and B? In B, SiO2 is removed.
And figure A said there is no SiO2 in the right edge. I mean the resist is written out.
Why?
No SiO2.
Yes, if it is full of SiO2. Upper portion means?
Is the edge of resist. The junction. Second junction. There is no SiO2.
No, it is full of SiO2. The whole surface is coated with SiO2. then the photoresist is covered, sprayed on the surface. So, the difference between A and B is only one difference is there. Here there is no SiO2 on the mid region. Okay. Otherwise, there is no difference. Only from the mid region the SiO2 is removed. Then the difference between B and C, you see that on C there is no photoresist on SiO2. There is no photoresist on SiO2. Okay.
Where is the hardened photoresist?
Where is the?
Hardened photoresist
It is gone.
in the first step or?
It depends on the photoresist nature, whether it is negative or positive. Suppose the hardened was on the mid portion, suppose. So, it is gone in the first step, or if you think that the hardened region is on the side portions, then now it is gone, on C it is gone. So, it depends on the nature of the photoresist.
What is the significance of a hardened region?
No, it is, there is no significance except that it is a chemical property. For that particular type of hardening or softening, you will have to use different kinds of chemical etchants to etch it out. Okay. Like in many cases that we have discussed, say you would like to clean a silicon substrate. So, there can be a etchant of acidic base or there can be an etchant of alkaline base. Both acidic and alkaline base etchants can be used to remove the oxides layer from the silicon. Different kinds of solutions and etchants are possible. Similarly, different kinds of photoresist are also available in the market. So, consider that if the mid portion has hardened, so it has gone on the first stage. Now, if you consider that the mid portion, the soft portion has now gone. Okay. So, now what you see that on N silicon we have defined one region at the mid portion, say 1 centimeter by 2 centimeter, example in this case, and on the left and right of it, it is full of SiO2. Now, when it is diffused, some species is diffused on it, say boron is, we would like to diffuse boron on it, then what will happen? The boron will not be able to diffuse on the SiO2, only it will diffuse at the mid region. So, this P silicon, you see that P silicon is formed here only, the P silicon is formed here only, though there is some extension of the junction below the SiO2 that we have discussed during our discussion on diffusion and ion implantation, why such thing happens. Okay. So, that means you have restricted the diffusion or ion implantation of the P type material on the SiO2 regions. So, that means through SiO2 nothing will be penetrated, only there is no SiO2, there will be penetration of the dopant gas and p-n junction will be formed. So, this is the formation of p-n junction, and on the rest of the figures basically there is metallization, because without metal contact the current will not be able to pass through the junction. So, on the top and on the bottom there will be metallizations, and that is basically aluminum in nature. And now, this, what is the size of this p-n junction? Say the size is 1 centimeter by 1 centimeter, or say 10 centimeter by 10 centimeter, that means length and breadth. Then you have to cut it into small pieces to form one device. That means one device is some micron square. So, if it is 10 centimeter by 10 centimeter, that is 100 centimeter square area. So, divided by say 0.1 micron square. So, you can assume that how many devices will be formed using a 10 centimeter by 10 centimeter junction. Okay. So, that is, yes, your question.
So the penetration of charge.
Not charge, the penetration of the dopant gas.
Yes.
Yes.
With the acetone there is
Through SI, no, that is not possible. Even ion implantation is not possible. Even ion implantation is not possible. No, not possible. Then no, then you have to, yes, then you have to thicken the layer SiO2. You have to thicken the layer SiO2, but a MOS principle is different. MOS principle is not this principle. Okay.
In that case, the charge is transferred from metal to semiconductor.
Yes. Yes.
Why it is possible?
No, that is a different story. MOS principle we are not going to teach here. No, that is a different kind of principle. That is a parallel plate capacitor.
Principle is different, but I'm talking about how it penetrates through the SiO2.
That is the electron is penetrating. Here arsenic atom will have to penetrate. No, arsenic atom is not a charged species unless it is ionized. Unless it is ionized. Okay. Unless it is ionized. Generally for n-type doping you use arsenic. So, arsenic atom is diffused, and this diffusion is basically due to carrier concentration different. Diffusion is basically the carrier concentration different. Yes.
So what type of contact is in between
What type of?
contact in between metals and semiconductors?
Yes, metal and semiconductor contact will be different, will be discussed separately. There can be two types of contact, one is the ohmic contact, another is the Schottky contact. Okay. So, those things will be discussed separately, possibly within next 3-4 classes. Yes.
Here that means you are doping with PJ, then it pushing the in dopant.
No, it is not pushing, because you know that the mechanism of doping is that it is taking inside the crystal lattice. So, there is no pushing or pulling in case of semiconductor doping. It is they are forming the bond, and where they go, we have discussed this thing earlier also, vacancy. So, if there is vacancy, there will be, yes. If there is no vacancy, there will be no diffusion, but fortunately there will be sufficient vacancy in the crystal. And so, if your stomach is empty, you can consume. If your stomach is not empty and if you try to consume something, then there will be some pushing type of thing. Otherwise, why there will be pushing or pulling? Yes, please tell.
Point is that it's already in dope.
Yes.
Then I am putting PJ.
No. So, where it is going, the atoms are going on the vacancy. So, if there are sufficient number of vacancy, it will go there. If there is no vacancy, it will not go. Then there will be, you have to energize for creating the vacancy, and those things we have all calculated also, how much energy is required. Okay. Yes.
First we have developed a photoresistor.
Yes.
Finally, in the third step you remove the total photoresist.
No, because you have defined a junction. For defining a window, you have used that type of a thing. Okay. That is the reason that you have used the photoresist. Otherwise, how you will define this junction without photoresist? Actually, the photoresist was given to remove silicon oxide SiO2 from a certain portion, which we have done, and then we have doped. Okay. Now, so far as the contact is concerned, generally the whole surface is given the metallization. It is done by thermal evaporation technique, we shall discuss separately, and what type of metal we choose, why aluminum is chosen for silicon, why if you use gold it will, or platinum, it will be Schottky type of contact, why those things happen, that we shall discuss separately. Now, in our PN junction device, you know that on the principle of PN junction many devices are formed. Say this is a P and this is N. For P, where is the Fermi level? The Fermi level will be here. For N, where will be the Fermi level? And say this is the metallurgical junction. It is the metallurgical junction. that means this side P, this side N. It is before contact. Okay. Now, when you make the contact, what will happen? When you make the contact, what will happen? Fermi level will why?
There is a clock transform and that
Yes, Fermi level is constant, but why?
So it's not constant, we just take the Fermi level at equals.
But why you take?
Because no current flows between two portion of this. If there is some difference, if charges are flow from one to
Exactly, exactly. So, now what will first happen? Here in P side, say boron atoms are there, you have doped P side with boron atoms. So, there will be many boron atoms. And on the N side, say it is phosphorus atoms.
So we can't do boron and phosphorus.
You cannot. Boron is for P type and phosphorus is for N type.
For p-type doping, for
Boron, aluminium,
I think we can't dope phosphorus for n-type.
why? Why you cannot do?
I have read
Phosphorus is the pentavalent atom.
Yeah.
You can. You can. So, in this case, due to ionization of phosphorus, a phosphorus atom will be ionized and one electron will be donated to the crystal lattice and the phosphorus atom will be positively charged ionized pieces. Why? Because leaving of electron or absence of electron is considered as the positive. So, it will be positively charged, it will be positively charged, it will be positively charged. Okay. Similarly, boron, it will be negatively charged. Why? Because positively charged particles holes will be donated to the crystal lattice. So, in this diagram, you see that the electrons are the majority carrier on the N side and holes are the majority carrier on the P side. So, what you have suggested that there will be diffusion of charges from the higher concentration region to the lower concentration region. So, that means electrons will move from N side to P side and holes will move from P side to N side. And very near to this metallurgical junction, they will recombine. They will recombine. So, that means on the vicinity of the metallurgical junction, on the region close to the metallurgical junction, there will be depleted of charge carriers. Depleted of charge carrier means? No, not neutral. Depletion means very few. Depleted of here means some here are left, but almost there is no here. Depletion. Okay. So, this region is known as the depletion region. This region is known as the depletion region. Why? Because this region is depleted of free carriers. Here there are free carriers, electrons are the free carriers. Here there are free carriers, holes are the free carriers. But near the vicinity of the metallurgical junction, it is depleted of free carriers. That is why this region is known as the depletion region or pace charge region. Pace charge region. Why? Because when there will be recombination, only the ionized donor or acceptor will be there, because it is also here on the both sides of the metallurgical junction, there will be the ionized dopants and acceptors. not only here, it will be here also. So, just at the adjacent to the metallurgical junction, there will be two column of charges. On the N side, it is the positively charged donor, on the P side, it is the negatively charged acceptors. So, that means two column of charges will be there. So, since two column of charges are there, so that will give to an rise to an electric field, because under this circumstance field is there, uncovered charges are there. So, electric field will be generated. So, this electric field, what will be the direction of electric field?
Right here.
Why? It will be directed always from positive to negative. It will be directed always from positive to negative. So, the electric field will be generated, and that electric field will prevent further diffusion of charge carriers from N type to P, N region to P region, or from P region to N region. So, that means when the electric field will be generated, that we shall see that a built in potential will be generated also because of that field. Okay. So, diffusion will be stopped. You take a P type material, you take an N type material, you join it, there will be diffusion. How long the diffusion will take place? So long as the electric field will not be there. When sufficient electric field will be generated, further diffusion will be stopped. Now, the question comes, then how the band diagram will look like? The band diagram of a PN junction, how to draw it? The band diagram of PN junction will be like this. What is the difference between this one and that one? Here you see that throughout the material there is only one Fermi level. There is one Fermi level throughout the material. It is aligned. Single Fermi level. Here there were two Fermi level. Here this is EFN, which was just below the conduction band of the N type, and it is EFP, which was just above the valence band of the P region. There are two Fermi levels were there for two different regions. Here the Fermi level is aligned, and that thing you have suggested also, he has suggested also, because if there is any discontinuity of the Fermi level, that means their change of energy is associated. But without doing any work, such change of energy is not possible. So, the Fermi level will align itself when it will be in equilibrium. When it is in equilibrium? When the electric field is sufficient to stop further diffusion, then we can say that the junction is in equilibrium. Okay? When the junction is going to be formed or during diffusion, it is not in equilibrium, because there is movement of charges from one region to another region. Okay. So, equilibrium is reached at that time, at that point of time when there is no further diffusion. During equilibrium, the Fermi level will align itself throughout the length of the material, and you see that there is a band bending. Have you seen the band bending? You see that this is band bending. In this region, band bends. Band bends. Why band bends? Why band bends? Yes, it is because of the concentration of free carriers. You see that when there is a depletion region, the free carriers are very small. So, let us consider this case that here the charge carrier is 10 to the power 15, here charge carrier is 10 to the power 16, here charge carrier is 10 to the power 18, here charge carrier is 10 to the power 20. Say it is n type material, it is conduction bandage, it is valence bandage. So, what should be the Fermi level? For 10 to the power 15, say it is here, 10 to the power 16, 10 to the power 18, more close, 10 to the power 20, sufficiently close. That means, Fermi level changes as the carrier concentration changes. Since near the depletion region or inside the depletion region, the charge carriers are less. So, this will be more. That means, the difference of the Fermi level with the conduction band will be more. So, that is the reason that since to align the Fermi level, the band will bend itself. Fermi level will not bend, Fermi level will be in thermal equilibrium, it will be constant throughout the material. So, to denote the change in carrier concentration in the material, what is the option? Band will be bent, right. So, that means you see this is the metallurgical junction, on both sides of the metallurgical junction you see that the band bends. So, that the carrier here it is n type material. So, carrier you see that the Fermi level is very close to the conduction band. Here it is p type material, it is very close to the valence band, but on the depletion region, what is the difference? You see the difference is more, the difference is more, the difference is more, the difference is more compared to this region. Why? Because the charge carrier concentration is different. So, that is the reason band bends in thermal equilibrium. Whenever we would like to draw a band diagram in semiconductor, in metal semiconductor contact we shall also again draw the band diagram. In FET, MOSFET, every time in transistor you can draw the band diagram. In heterojunction of junction between two dissimilar semiconductors, you will draw the band diagram. Care must be taken when it will bend, where it will not bend, where will be the Fermi level. So, that means all those parameters you must know. To draw a band diagram, what are the parameters you must know? One is the band gap, number 2 is the carrier concentration. Okay. That means the band gap you know, if you know the band gap you can know the type, because it will be not unknown. Suppose you have grown gallium arsenide on silicon, so you know that you have used the p type silicon and n type gallium arsenide you have grown. So, what should be the band diagram for p silicon and n gallium arsenide? Because the carrier movement inside the material will be governed by the band diagram. Unless you do not have any knowledge about the band diagram, you cannot think where will be the electron at what moment, whether electron will movement will be there or not. So, now this you see that this is the difference between the bottom of the conduction band in n side to the bottom of the conduction band in the p side. Okay. This is known as the built-in potential. Built-in potential. That means, as soon as the thermal equilibrium is reached, then what you find? As soon as thermal equilibrium is reached, the electrons movement will not be possible. Why? Because there is a wall, there is a barrier. Now, if electron moves from here to here, what we will have to do? You will have to cross a barrier of energy EV0. Unless the electrons are energized with EV0 amount of energy, electrons will not be able to escalate the barrier, to reach the barrier, or to cross the barrier. Okay. This is known as the built-in potential, and why there is a built-in potential? It is because of the electric field generated because of the uncovered charge in the depletion region, which stopped further diffusion from N side to P side or from P side to N side. Okay. So, that is very important consideration for p-n junction. Now, if you forward bias it, make it forward bias. What is forward biasing?
Make P is positive with respect to
P type at higher potential and P type at higher potential and N type at lower potential.
Yes. So, that means it is forward bias. Why it is forward bias? Because P is connected with the positive terminal of the battery and N side is connected with the negative terminal of the battery. When the positive terminal of the battery is connected to the P side and negative terminal of the battery is connected to the N side, then it is known as the forward bias. Under such a circumstance, suppose the bias is V, V volt is applied, then what will happen? What will happen? What will happen?
the majority of volt is coming inside.
No, what will be happen to the band diagram?
Okay,
Yes.
Depletion width will be
Which will increase.
width will decrease.
decreases.
Yes,
Forward bias, no?
weight will decrease. That means EV0 will now be EV0 minus V. EV0 will now be EV0 minus V. Okay. Why? Why such thing will happen?
Because then these two terminals will push the carriers through the depletion.
No, actually physical significance is not that thing. The whole voltage, V amount of voltage will be dropped at the depletion region only. Why? Because away from the depletion region, in the bulk region, basically on this side or that side, it is conducting in nature. It is conducting in nature. So, the drop of voltage drop will not be there. Where there is a voltage drop? Yes, when there is a resistance. Forget about depletion. Depletion, the term we are using for p-n junction, but normally where the voltage drops, when there is a resistance. So, here the depletion region, since it is the depleted of free carriers, so that means the resistance must be higher than the bulk regions. So, the whole voltage will be dropped on the depletion region. So, it will be E V0 minus V. So, this thing will be, now the band diagram will be like this. This is E V0 minus V. Earlier it was like this. Earlier it was E V0. Okay. Earlier it was E V0. Now it is E V0 minus V. That means now the electrons will be able to surmount the barrier and there will be movement of electrons from this side to that side, and similarly the holes from this side to that side. Here remember that this is also again diffusion of electrons. Again this is diffusion of electrons, because on the n side the electrons are larger in numbers, and also since you have connected the negative terminal of the battery with the n side. So, that means the electrons which are getting out from n region is being compensated by the negative terminal of the battery. That means, at the cost of the battery, at the cost of the energy, from where the energy is coming? From the battery. Okay. So, basically you are losing energy of the battery to compensate the charges which are diffusing from n to p, because how many charges are there on n region? Say n x amount of charges are there. So, x amount of charges will go on moving. Okay. So, after x amount of charges leave n side, from where the charges will come? From the battery. Okay. So, that is the whole physics behind this p-n junction, that when you put a forward bias voltage of amount V, it will act on the depletion region and it will be E V 0 minus V, again the diffusion of electrons will be there or holes from there. That means, now the band diagram will look like this. Remember that now there will be no alignment of the Fermi level. Why? You have broken the equilibrium, because you have connected a voltage source. So, you have broken the equilibrium. Only during equilibrium there will be alignment of Fermi level. Okay. Now, this amount is E V 0 minus V. So, diffusion of electrons will take place and holes will diffuse from this side to that side. This is diffusion. So, because of the diffusion of carriers, you will have a current which is known as the diffusion current. Similarly, there will be drifting as well. What is the drifting? Drifting is, here there will be electron, that electron will drift from this side to that side. You can ask me, sir, why there will be electron? Minority carriers will be there, and some minority carriers will be thermally generated also on the p region. Okay. So, electrons will move from, there will be the diffusion, drifting of electron from p region to n region will also be there. In thermal equilibrium, drift current equal to diffusion current. So, there will be no resultant current available from the device, from the junction.
Drifting of electron from N to P
No,
in forward bias.
no,
Diffusion explains
diffusion from that to that side, drifting from the other side. Okay. Now,
Current direction is from P to N.
see, I know everything. Problem is also, no, we are discussing the drift and diffusion. We are not considering the whole device right now, that we shall discuss in my next class, where I shall show you a mathematical calculation, what is the value of drift current, what is the value of diffusion current, and what is the total current, that we shall discuss. Okay. Now, so the current will have two component, one component is diffusion and one component is drift. In thermal equilibrium, the drift and diffusion current are equal and in opposite. So, there will be no resultant or total current in the junction, but as soon as you will put the voltage source, so then there will be different amount of current and drifting will be larger than the diffusion current. Okay. So, similarly, it will be for electrons. Similarly, for holes also there will be diffusion and there will be drift. So, electron will have two components, one is diffusion current and another is drift. Similarly, holes will have two components, diffusion and drift. In our next lecture, we shall derive the expressions for the diffusion and drifts current for electrons and holes, and we shall see the total current through a p-n junction with some forward bias, or if we connect some reverse bias. In reverse bias, the opposite thing will happen, that means yes, and in that case the depletion region will be widened. So, there will be no current, only there will be reverse saturation current or current due to the minority carriers. We shall discuss that thing. Okay, thank you.